Hey guys, let's go ahead and talk about section 3, exponential and logarithmic models. Here we go. So important bell-shaped curve. It's the graph of a Gaussian model. And we'll talk more about what a Gaussian model is. If you want to look up a really cool mathematician, look up Gauss. A logistic curve is the model that describes populations that initially have rapid growth but it's followed by a declining rate of growth. And then sigmoidal curve is just another way, or AKA also known as logistic growth curve. Okay, so an exponential growth curve model is y equals a times e to the bx, where b is positive. An exponential decay model is y equals a times e to the negative bx, where b is also positive. So basically that the b value is multiplied by a negative, so it's a declining. The Gaussian model is y equals a times e to the negative x minus b times 2, or excuse me, squared, pardon, it's going to be a little bit exponent. So squared, and then everything over c in the exponent. Okay. So, and then the logistic growth model is y equals a times a over 1 plus b e to the negative rx. And the logarithmic model is y equals a plus x times the ln of x. You can also say y equals a plus b times the log base 10 of x, depending on which type of log you're talking about. So let's talk about exponential growth and decay. So suppose a population growth according to the model is p, which we know is the amount is the 800 initial amount times e to the 0.05 t. Remember that 0.05 would be the rate, where t is given in years. What's the initial size of the population? Remember, the initial size is that initial value that comes before the e, so that's 800. And then how long will it take this population to double? So if the initial value is 800, double that, the double value would be 1600, right? So if I want to know how long it takes to get to 1600, that would make the amount be 1600 as the amount equals 800 as the initial times e to the 0.05 t. And we're going to solve for the amount of time it takes. So we used natural logs and logs, so we can solve this. So first thing, in order to get t by itself, we're going to divide by 800. So 16 over 800 is 2 equals e to the 0.05 t. To get e out of the way, to get t by itself, we're going to take the natural log of both sides. That will cancel. We get 0.05 times t equals the natural log of 2. Divide both sides by 0.05. And we get t as approximately 13.86 years. Okay, so that's how we would solve that population growth for the time. And then to estimate the age of dead organic matter, scientists use a carbon dating model that says R equals 1 over 10 to the 12th times e to the negative t over 8245, which denotes the ratio R of carbon-14 to carbon-12 that presents at any time in years. So for example, if the ratio of carbon-14 to carbon-12 in a fossil is 10 to the negative 16, let's find the age of the fossil. So to find the age of this fossil, we're still going to use big R, which was 10 to the negative 16, equals 1 over 10 to the 12th times e to the negative t over 8245. Again, we're solving for t. So in order to solve for t, we're going to start to move things away. So in order to multiply or to get that 1 over 10 to the 12 away, I'm going to multiply by 10 to the 12th to cancel it out. What that does is I'm going to have to multiply it on both sides. Remember, base 10 to the 12 times base 10 to the negative 16 is base 10 to the 12 plus negative 16, which is negative 4, equals e to the negative t all over 8245. We're still going to get the t by itself, so we're going to take the natural log of both sides. That will cancel out the e. So I'm ending up with the ln of 10 to the negative 4 equals negative t over 8245. To get t by itself, we're going to multiply by negative 8,045 on both sides, 8,245, excuse me. And so we end up with t equals negative 8245 times ln to the ln of 10 to the negative 4. And we get approximately, because we're rounding here, 75,737 years. So that's how old that fossil would be using that carbon dating model. So talking about Gaussian models, the Gaussian model is commonly used in probability and statistics to represent populations that are actually called normally distributed. If you ever take statistics, you'll hear this term all the time. And that's what that bell curve looks like. On a bell-shaped curve, the average value for populations is where the maximum y value of the function occurs. So if this is our maximum y value, the shape of the model looks like this upside down bell. That's called a bell curve. And that's how we draw the basic form of a Gaussian model. For logistic growth models, if we wanted to give, remember, logistic was when it starts to grow a lot and then something happens and it has a decreased rate of growth. An example of that could be like bacteria growth. And that would be like, let's just say bacteria growth in the summer. In the summer, it's warmer temperatures, and it is high humidity, often around the country. Maybe not so much around here, but around the country. Whereas in the winter, the temps go to freezing, and it is dry weather, not so much the humid weather. So bacteria that thrive in warm, high humidity in the winter would decrease that population. It's not going to produce so rapidly. And if I were to draw that basic form of the graph for logistic growth, it would look something like this, where it kind of rapidly grows and then it tapers off. So that's our logistic growth model. And then, so if we were going to solve a logistic model, let's talk about the number of example kitchen widgets. So something that you use in the kitchen, where y is in millions demanded each year is given by this model, where x is 0 represents the year 2000, and x has to be positive. So find the year. So they're asking for find the year x in which the number of the kitchen gadgets demanded was 8.6 million. So we're going to use this. So instead of y, we're going to use 8.6 million equals 2 plus 3 times the natural log of x plus 1, where x is in the year 2000. Well, if 0 was 2000. So I'm going to start solving, and I get 6.6 equals 3 ln x plus 1. I'm going to divide both sides by 3. And so I get 6.6 divided by 3 is 2.2 equals the natural log of x plus 1. And then we're going to remember how to cancel out an ln, we're going to raise it by an e. So that cancels. We've got e to the 2.2 power equals x plus 1. To get x alone, we're going to subtract the 1, and we get x equals e to the 2.2 minus 1, which is approximately where x is 8. So if x is approximately 8, that's the year 2008, because if x was 0, that was the year 2000. So that's the year 2008. Okay, that's it for today. I'll see you back in class.